Alrighty, so this is the recap of lecture number 7. And at the very end of lecture 6, we started tackling the different scheduling algorithms that exist out there. And we said that we're focusing on the short-term scheduler, also known as the dispatcher. And these are the scheduling algorithms that are concerned with the dispatcher. And we said that we have two things to answer when it comes to scheduling algorithm is to know which one to pick between available processes, the available ready processes, of course, because we pick them up from the ready list, and then this is what we call selection, and the timing of the selection. So when is the selection needs to happen? And we've seen that we have preemptive and non-preemptive. And in one word, preemptive means that a scheduling algorithm allows the dispatcher to kick out a process from the CPU, out of the CPU, even if that process is not done using the CPU yet. Alright, this is the whole preemptive paradigm. And naturally, non-preemptive means that once a process is inside the CPU, nothing will get it out until it's either done or it's being blocked over a resource or something like that, right? But no other process can kick it out back to the ready state if it's not done using the CPU. Alrighty, and we've seen the first come first served, and we've seen if it's preemptive or not, and we studied the execution of it. And then we went to tackle the round robin, and we've seen that it's preemptive, for instance, and we were extremely interested in whether it's a fair algorithm or not, and most of the people assume that because we're assigning a time slice for each of the ready processes, so basically it feels like it's a fair fair scheduling algorithm. And I'm gonna circle back to that in a moment. Another scheduling algorithm that exists out there is called the shortest job first, SJF, and we're gonna check out if it's preemptive or not, and we're gonna see how it works. So basically, when I asked the face-to-face attendees what would that be, so basically most of them assume that I'm gonna go ahead and fetch between the ready processes the one that needs the CPU the least. So the ready process with the smallest execution time needed, so CPU burst time, I'm gonna call execution time or burst time, same thing, should be selected first. Fair enough. So let's see it here. So I have P1, P2, and P3. And one of the obvious questions that I ask all the time, well, go ahead, which one should go first? Well, I still have no information about anything, so I need the execution time. However, I have a very important information, which is the arrival time. So basically here we can notice that P1 was slightly here before P2 and slightly here before P3. So basically when P1 became ready, no other process was in the ready list. So basically P1 can go first, right? And I don't even need the information about the execution time of P1 because naturally it will go first. It was there on its own at the very beginning. However, I'm interested here, once P1 is executing, right, two of the processes arrived, and it's the case here. So once P1 is done, I need to make sure to pick one of those ready processes now. So if P2 has a big execution time and P3 has a rather small execution time, so which one should go first? So with the one with the shortest job, and in this case it would be P3, and then followed by P2. So is SJF preemptive or not? Well, you can notice that I did not in any way kick out P1 before it's done, so it's non-preemptive. Fair enough. So each and every time an execution of a process is done, I'm going to go ahead and look in the ready list which process has the smallest execution time. Well, and then we spent some time during the face-to-face lecture trying to think about a preemptive version of that particular scheduling algorithm, which is the shortest job first. And after a lot of back and forth and discussions and debates, extremely interesting and exciting, we concluded that maybe there's the preemptive version of it means that within execution here, I'm gonna go ahead and check which one still have the shortest needed time to fulfill its execution. Meaning that in time, you're gonna notice that P1 has, let's say here, P1 has already executed like partially half of it. I mean, almost half of it, right? So it still needs half of the original time it needed. And then I can compare what's the remaining time here to the other processes that are in the ready list. And if any of the other processes has a service time which is smaller than what's P1 still needs, well, P1 will be kicked out and that other process will take over, right? And the name of that algorithm would be, and it already exists, and the name of it is the shortest remaining time. And that's the preemptive version of the shortest job first. Alright, so I'm gonna circle back to the round robin, and I'm gonna give you a couple of things. I'm sure that you thought about it long time. So basically, there's the CPU burst time. This is what we talked about, the execution time, and we've seen that round robin is awesome when it comes to the CPU burst time, meaning that I'm gonna assign a time slice from the CPU's point of view to each of the processes that are present in the ready list. However, we've seen that sometimes some processes, well, they kind of need some resources. And as a generic statement here, I'm going to call, anything that is related to a resource, I'm going to call it for now, it's some IO weight. So if a process needs the printer, well, if the printer is not ready, so that particular process will need to wait on that printer, which is basically an IO device, so it's an output device. Alright, so not only I need the CPU per se as a process, but I might need some resources. So let's circle back to the round robin. So the round robin assigns a CPU time slice for each of the processes, but it doesn't even look at the resources. This means that for some reason, if let's say process number 2 is having its time slice, however, for some reason it needs to access one resource and that resource is not available, so it won't even be able to use the time slice, the CPU time slice that is assigned to it, because it will get blocked. So yeah, so now how fair is RR to processes with those processes that have big IO bursts? They need a lot of IO and they might get blocked over those IOs. So you can see that it's not that fair with those processes. However, it's extremely fair if all the processes did not need any resource. So if all processes only needed CPU burst time, round robin will be extremely the fairest of them all. But that's not the case in real life, right? And expect to have a lot of analysis like this type of analysis later. Alright, so we're gonna move on now, and what I've done in class is I've showed this picture and I asked someone to try to understand what kind of scheduling algorithm here I'm trying to propose. So here someone said that they're seeing three queues, three lines here, and there's the keyword priority. So basically the scheduling algorithm that will be discussed on on that slide is priority related. And here you can see that we have different priorities. So it feels like a process will be assigned some priority and multiple processes can share the same priority. So hence we can organize them in a queue here, and any mechanism, it could be anything, first in, first out, or random, doesn't really matter. And then, well, if a process has an extremely high priority got into the ready list and another process with a low priority is executing, naturally the one with the highest priority should kick out the one with the lowest priority. So priority is here to enforce preemption, n'importe quoi, preemption. And the one of the examples that I keep on using, I don't know if I already used it online, but I mean in my face-to-face lectures, is that imagine that you have a computer in your car, so a single computer in a car, and this is of course just an illustrative, this is not real life, but I mean a car with a single computer that runs two things, the radio and the brakes. Fair enough. And there's a process that deals with the radio, of course, and there's a process that deals with the brakes. So basically, when you're listening to the radio and you just wanna stop the car, emergency stop your car, you're gonna go ahead and push the brakes, and you're expecting that whatever the computer is executing should be kicked out. So basically, if the radio is being playing, and you just initiated the process that deals with the brake, well, at any cost, the process with the brakes should execute with the extreme high priority. Alright, so here we are having three processes, and let's do some analysis here. So which one should execute first? P1 being the one with the lowest priority, and most probably P3 is the one with the highest priority. I think, I have no idea. I still have no information about that for now. But I mean, given the information that we have to now, which one should execute first? Well, you guessed it right, it should be P1. How come? Because you can notice that it is the first one to arrive. So when it got to the ready list, there were no other processes. So this one naturally will be selected first. Now, high priority for P2 and medium priority for P3. So P1 will execute first. Whoops. P2 got into the ready list. It has a way higher priority than P1, so it should kick it out and execute. And then, while executing, P3 got ready, arrived, and then you can notice that we continued with P2. How come? Because the priority of P3 is lower than the priority of P2. Preemption, because P1 is not done yet. It was kicked out. Here, there's no preemption. Now the question is, once P2 is done, which one should execute? Should I resume P1 or should I execute P3? Well, I'm going to compare priority of P3 to the one to P1's priority, and you can notice that this one has a lower priority than that one, so it should be P3. And then once those are done, this one is done as well, well, I can go back and finish up whatever I started with P1. Fair enough? So it's definitely preempted preemptive scheduling algorithm. Fair enough? So yeah, I'm gonna assign a fixed priority. You can notice that every process will have a fixed priority, and one process could have, different processes could have the same priority. So I need to organize them in a way or another, if it's the case. So this is a fixed priority. Now, keep that in mind, and let's move on to the next slides, because you're gonna get inspired from this one in order to be able to answer the next one. So check this out here. Take a second and let's move on. Right? Do you see any difference? yes, it feels like something can move now from one queue to another. This means that I can have a high priority, and then for some reason I can see my priority gets lower and lower, etc. So let's keep in mind what, let's reminisce the things that we talked about a slide earlier. So we were talking about a fixed priority then, and here it feels like a priority can change. It's not fixed anymore, so it's some kind of dynamic priority. Right, so let's see again, 3 processes, with P1 being the lowest priority process and P2 and P3. Naturally, which one should go first? We're gonna check the arrival. P1 got here first, so basically P1 will execute first. Right, so P2 now is there. It has a higher priority than P1, so it should execute. Right, so let's see what happened here. So P3 got here, it was ready whilst P2 is executing, and P1 is still not done. In the previous example, we've seen that it should go to P3. However, in this example, we're seeing that we're back to P1. So this means that for some reason the priority of P3 was lowered, so it's a dynamic rate. It was lowered to be able to let P1 execute for now, and then I can execute P3. Now the question is, why would I lower the priority? Why would I make it leave? Well, there could be so many reasons. One of them could be the deadline. So basically, maybe the deadline of P1 is way closer than the deadline of P3. This is why I'm moving, I'm changing the priorities of those things. And we're gonna see concrete examples in the real-time embedded systems course next year. Fair enough? So processes can move between queues, and this one could be either preemptive or not preemptive, and the version that we're looking at here is definitely a preemptive version. I mean, not usually speaking, if we're using priorities, it's because we want it to be preemptive. However, of course, as anything, it might exist, a non-preemptive version might exist as well for some reason. Right, so this is dynamic priority. Right, so unless I say otherwise, we're dealing with a monocore, a single core computer. Well, now if we have a multi-core, so we need to deal with scheduling as well. Would it be more simple or more complex to deal with multi-core? Well, naturally it will be more complex, because you can think about the stuff that I need to synchronize and coordinate, etc., etc. Right, so when I have multiple CPUs, the beauty of it, it's like I can physically assign a process to a processor. So I can have different processes running on different processors at physically the same time, as inexorably the same time. So I can have some load sharing. Instead of having only one core executing everything, well, I can distribute now the processes over the CPUs, and I can share the load. And we're gonna see why it's complex. Giving an example from my research, more than 10 years ago, a little bit more than that. And this is an example from computers in a car, and here you can see 2 different computers, and here we can see the different processes that need to run on those computers. Fair enough? And these are the physical computers, and then we have sensors and actuators in order to be able to communicate with the outside world. Well, to give you just an overview about the example that you're looking at here, this is called a steer-by-wire. So basically, it's the automotive version of the fly-by-wire. So in the 70s, approximately, with Airbus, in planes, instead of having mechanical chains and to be able to fly the planes, well, all you have to do is handle a joystick on the plane, and then everything is you know, electronized in a way or another. So it's everything has become electronic and electromechanic. So you don't have full mechanical chains anymore. All you have to do is easily handle a joystick, and then you have some hydraulic pistons and you know, electromechanic devices that will deal with that. And because the automotive industry is usually around 10 to 15 years late compared to the technologies that are being used in the aeronautical and the airspace industry. So the people decided that we want to have a system that is you know, that resembles the fly-by-wire system, and they called it steer-by-wire. So the steering wheel is not mechanically chained to the actual wheels, to the, you know, rolled wheels anymore, and you can have you know, it's easier, so you have some driver's assistance, etc., etc., and it feels lighter for the user, for the driver, which is the user. And it has the mechanical chain has been replaced by wires and naturally computers, sensors, actuators, etc., to make it happen. Of course, in order to be fully functional and accepted, it should be legalized first, and this is a long process, especially in Europe. To make a long story short, so here we're seeing the steer-by-wire, and we can see that we have two computers, as I said, and we have a bunch of processes that need to run. Some of the processes will be dealing with some IOs, right? So some sensors and actuators. So some sensor could be there to feel the steering, and some actuators could control the wheel, for instance. So this is why am I using this as an illustrative example? To you know, to show you why it's complex. So basically, you can imagine if I need to assign to schedule the different processes on the different computers, you know, on the different cores, the CPUs, well, I need to carefully choose the process that needs to deal with a particular sensor on the computer that is physically attached to that sensor. Because if it's not the case, well, you can see that, well, this will create a lot of problems, synchronization, and, you know, how to make the data go from one computer to another. So we have a lot of constraints and things to take into consideration in order to be able to say that, well, this process should go on that particular processor. Fair enough? Alright, so let's see how we could make things simpler. You know, not very simple, but simpler. So the first approach to multi-processor scheduling is to assign the kernel on one CPU, and then any other, so all kernel processes will run on one CPU, and any other user processes will be distributed among the other existent CPUs. And here in this case, you can see a 4-core, for instance, where the first core deals with the kernel, and then the other 3 cores are dealing with user processes. And this is what we call the master-slave approach, where you have one master that, you know, dictates in a way or another the things that need to be done on the other cores. Fair enough? The beauty of that, we don't have to talk too much, to synchronize too much, because it's a one-way ticket. It's a directive. You don't have to communicate a lot in order to synchronize. It's, you know, it's being unidirectional. And this is what we call a asymmetric multiprocessing. Fair enough? So we don't need a lot of data sharing here because it's commands coming from above. Kind of reminds me of one system. Bon, bref. So if I'm telling you that there's an asymmetric multiprocessing, well, what would be the second approach? Naturally, a symmetric one. So we can have different CPUs with the same, and, you know, being at the same level. So you don't have a unidirectional approach anymore. Well, it's now you need to communicate and deal with everything and synchronize and talk to each other, etc., etc. And you can notice that in that particular example as well, that the kernel is kind of, the kernel processes are kind of distributed over all the CPUs here. One of the beauty of this approach is that in the master-slave approach, if the master is done, you're done. If the master is dead, well, you cannot deal with anything anymore. And this is why sometimes we implement redundancy, so we can have a backup master, etc. But in here, the beauty of it, you can notice that, if processor A is dead, physically dead, well, you can still run some functionality. Well, it depends on your luck and on the things that are actually being here. So this is a symmetric. And instead of having one decision maker for everyone, well, each one will be dealing with the processes as a, self-scheduling processor. So basically, the kernel, the dispatcher, for that particular one will admit something and deal with it, and that the kernel, the dispatcher for that particular one will deal with a different scheduling algorithm. It could be anything. You can imagine different scenarios here, right? So there's no one master and commander for everyone. All right. So unfortunately, I cannot show it to you here on the video because I need to access the task manager. But in class, I've showed them. Maybe if you attend the next lectures, ask me to show it to you, how to set processor affinity. So basically, when you have a bunch of cores that are available for you, well, when you start the task manager, go ahead and try it at home, by the way, if you're watching on your computer, on a Windows computer, for instance. No, on a computer that is running a Windows operating system. Yeah, we're gonna get technical from now on. You can go ahead and start the task manager and go to the apps, go to the different tasks processes, and if you right click on one of the processes, there's something where you can set the affinity of it. And when you do that, well, you'll have a choice. When you click on it, you will have a choice to use, you're gonna tick one of the available cores for you. You can choose on which core you want your process to be running on. Why would we do that? Well, for so many reasons. Maybe we want to make sure that for some processes we want a dedicated core for them, and I don't want them to get mixed with other processes. For instance, for some reasons, if I'm playing a game, and the game there's a process that is dealing with that game, so I'm gonna go ahead and assign it on one processor and kick out all the other processes and put it on the other cores, for instance. Fair enough. We can either do some real load balancing here, so I can really distribute the different processes over all processes, whether the kernel or user, on the different processors. So I have so many options here. I have more flexibility here. However, you can see the problem here. It's I need to coordinate more, to synchronize more, and to share a lot of data to be able to make sure that the system is up and running. So yeah, it could be a little bit slower performance-wise compared to one way to get, if the master slave is well designed, it could go faster because we're not sharing a lot of that. It could. It's not a guarantee. Alright, so let me give you a taste of what you're gonna see with me if you're still around, and if I'm still around next year. Real-time scheduling. And here we have a lot of constraints, like real-life constraints. And we have strict and imposed deadlines that need to be respected at any cost. At any cost, in the sense of, if you miss a deadline, well, the result could be an accident or a catastrophe or a plane crashing or a car crashing or something like that. And real-time systems are usually the systems that you can find in planes, in space shuttles, in trains, cars, of course, in smart homes, and virtually anything that is wearable, anything that, Tesla cars, etc. All right, so here you can feel that I'm insisting on the deadlines. And yeah, one last thing is processes are sometimes are not sometimes are usually called tasks, and this is what we're gonna see next year. Tasks in real-time systems, and you can notice that the OS in real-time systems called an RTOS. So what would the RT stand for here? Well, real-time. So real-time operating systems, right? And tasks are usually periodic, and this is a question that I asked in the face-to-face lecture. It's an important one, I believe. Why would they be periodic? And someone surprisingly answered in a very positive and assertive way. It's, well, if we're dealing with in real time with the environment, so I need to keep on listening to the environment in a way or another. So periodic means that, well, I'm always there, I'm always coming back to check if something has changed, etc. And this is extremely important if I'm dealing with the environment that is surrounding me. And I asked a question, as all of you, most of you, are software engineers by now. I mean, with all the Java that you've done till now. So how would I implement something that is periodic? What would that be in a way or another? So a periodic task would be something that will always come back and it's never done. So how would I implement software-wise something that is never done? A loop, yes, definitely a while infinite loop. And then for it to be periodic, maybe I can make it sleep in a way or another. Don't worry about that, we can tackle it in more details next year. So here you can see the different tasks, the arrival of the tasks, and according to importance, well, you need to know which task to execute. And you can notice that the task, once it's done and it's respected its deadline, well, it's coming back. And sometimes it respects the deadline, sometimes it's cutting it short. But what we're gonna try and make happen in real-time systems is to strictly respect the deadline. So we need to have the appropriate scheduling algorithm that will strictly respect all deadlines for all tasks that are present in the system. And if it's not the case, well, maybe I need to respect at any cost the deadlines of the most important ones. So if there's this notion of importance, so what kind of scheduling, what would the scheduling algorithm be based on if I'm making sure that some VIP tasks are being, their deadlines are being respected? Well, you can feel that it's based on some kind of priority, and this priority could be based on, how critical my task is. So if one task is dealing with the brakes and another task is dealing with the engine control, so basically both of them are extremely important. However, for some reason the brakes should be a little bit more important if the deadline is too close, for instance. Fair enough? So you can feel it this way. And that's it, and hope to see you all soon.